In this video, we're going to talk about 8.2, integration by parts. And this is going to have an objective to find the antiderivative using integration by parts. This technique is useful in undoing the product rule. So if you remember the product rule here, if we took the derivative of product, it was u times dv dx plus v times du dx, or uv prime plus vu prime. Going to multiply all that through here to integration by parts is going to tell me that the integral of the derivative with respect to x of u times v is equal to the integral of this with respect to x is equal to u integral dv dx plus the integral of v du dx, like that. So u's not stuck here, it can pass through the integration symbol. So this is going to be equal to integral of u dv we want this piece right here is what we want to solve for, is going to be equal to uv minus the integral of v du. That's our integration by parts formula. Just memorize this. There's the reasoning behind it, that we can, like that, and we want u dv to solve for it, so it's going to be uv minus the integral of v du. There it is, right there. Memorize. All right. So if u and v are a function of x and have continuous derivatives, and the integral of u dv is equal to uv minus the integral of v du, this is going to be my given integral. That's going to be something that I can't simplify. Our goal is that this right here is a simpler integral that we can work with. So we want to turn integral of u dv into an integral v du to be an easier integral to evaluate. This is going to work with both definite and indefinite integration. So guidelines for integration by parts: try letting dv be the most complicated portion of the integrand that fits basic integration rules, then u will be the remaining factors of the integrand. Or try letting u be the portion of the integrand whose derivative is a function simpler than u, and then let dv be the remaining factors of the integrand. So specifically here, I'm not sure that I'm going to scroll through and see if we say this here. If not, I'm going to say it right now. Okay, so I like a little technique called liate. that helps me choose what should be u and what should be dv, so that I don't just sit here and guess. So I'm going to tell you about Liate right now in this space. So Liate. I'm going to choose u from this side and dv from this side. This is logs, inverse, trig functions, algebraic, analytic functions, algebraic functions. These are really power functions I'm thinking of, x to the n. Trig functions are here, and then exponential. Big idea here is these things to the left go away. Immediately when I take the derivative of them, it becomes simpler. Algebraic expressions that are polynomials and things like that are going to eventually go away if I take enough derivatives. If they're not polynomials, they may not completely go away. Trig functions and exponential functions. Trig functions, when I take derivatives, they keep coming back as trig functions. Exponentials always come back as more exponentials. Whether I differentiate or integrate them, they just kind of keep going around in circles usually. So we're going to have some examples of that later. So the only reason that I would want to differentiate a trig function is if there's an exponential in there as well. I always want to integrate the exponentials, don't want to differentiate them, because differentiating the exponential is never going to help me. So notes here, be sure you can tell the difference between your u and your v. I put a little tail on the end of my v there so that it's obvious. I try and make the tail down here on my u obvious. With your handwriting, that's not just important to your teacher for grading, but also important for you, so you can keep track of what you're supposed to do. And I recommend that you use a table. To help, I'll show you my table technique. dv will require integration. So you must capture the differential usually dx from the original integration on this term, and sometimes guideline 2 will fail. If it does, use guideline 1. All right, so very rarely will this Liate fail. So let's look at x e to the x here, dx. So if I use my Liate rule to help me choose, I'm going to choose my dv from this side, my u from this side. E to the x is in there, so that automatically makes that dv, and u is the remaining part, so du will be dx, and v will be e to the x. So there's my little chart I was talking about. Now I want u times v minus the integral of v du, and see how that simplified that integral there? So this is x e to the x minus e to the x plus c. Now we're going to look at Liate here. Liate tells me to definitely let that log piece be my u. dv is going to be everything else. So du is going to be 1 over x dx, and v is going to be x cubed over 3. So I want u times v, 1/3 x cubed ln of x minus the integral of v times du. And one of those will cancel, leave me with 1/3 x cubed ln of x minus 1/3 integral of x squared dx. Look at how nice that works. Now I have a nice u substitution where u is equal to x squared. Sorry, this is u to the n. So u is equal to x, du is dx, n is equal to 2. 1/3 x cubed ln of x minus 1/3 x cubed over 3 plus c, 1/3 x cubed ln of x. This should have absolute value bars around it, right? Yeah. No, it started off that way. And then minus 1/9 x cubed plus c. There we go. Next one here. So repeated use of integration by parts. We're going to have, let's look at Liate again to help us decide. So our trig piece is to the right of our algebraic piece. So algebraic piece becomes u, trig piece becomes dv. So du is 2x dx. V is going to be negative cosine of x. So uv minus the integral of v times du. It's going to be negative x squared cosine of x plus 2 integral x cosine of x dx. I'm still in the same situation where I don't have a simple integral here. So again, I'm going to let u be the algebraic piece and dv be the trig piece. Du is going to be dx and v is going to be sine x. So we have negative x squared cosine x plus 2 times, big brackets here, u times v minus the integral of v du. So this is going to be negative x squared cosine x plus 2x sine x minus 2 integral sine x dx. Be negative x squared cosine x plus 2x sine x minus a negative, this is going to be a negative cosine x plus c. Now an integrand with a single term, well, we know that that arc sine has to be u from Liate. We don't know how to integrate that. That has to be u. So the dv just has to be the dx. So when we take du, we get 1 over the square root of 1 minus x squared dx. V is going to be x. Now we have a definite integral here, so that's going to be a little different for us. We have x arc sine of x evaluated from 0 to 1 minus the integral 0 to 1 of x over root 1 minus x squared dx, like that. So 1 arc sine of 1 minus 0. Arc sine of 0 is also 0, so that's 0 all the way around, minus the integral 0 to 1 of 1 minus x squared x dx. U here is going to be 1 minus x squared. Du is going to be a negative 2x dx. So negative 2 then times a negative 1/2 out here is going to give me, so sine of what gives me 1? That's going to be sine of pi over 2. And then this is going to be plus 1/2 of integral. This is going to be du over root 1 minus u squared, or this is du over u to the 1/2. So this is u to the negative 1/2 du, like that. 1 minus 0 is 1. 1 minus 1 is 0. So let's go ahead and change those limits there. Change everything to the u world. This is going to be pi over 2 minus 1/2 u to the positive 1/2 divided by 1/2 is going to be times 2. This is 0 to 1. So that's pi over 2 minus 1 to the 1/2 minus 0 to the 1/2. It's pi over 2 minus 1 minus 0. It's pi over 2 minus 1. And that is approximately 0.571. Now, this is a fun one because it's going to loop around on itself. So I'm going to tell you that this one loops around before we get started. So I'm going to keep track of the left-hand side all the way down. I'm going to call this integral here I. And I'm going to hope that that pops back up in the problem later. It will. So I'm going to have part of secant cubed I can think of as the exact derivative of something else. That this is secant squared is the exact derivative of tangent. So I have an extra secant left over that when I take the derivative of it is secant tangent, like that. And so I is going to be equal to uv minus the integral of v du. So I is equal to secant tangent minus the integral of secant tangent squared. And we need to say 1 plus tangent squared is equal to secant squared. So tangent squared is equal to secant squared minus 1. I is equal to secant tangent minus the integral of secant times secant squared minus 1. I equals secant tangent minus integral secant cubed x plus integral secant x dx. There's my I again. So I equals secant x tan x minus I plus, and we know that this one is ln of the absolute value of secant x plus tangent x. So 2I is equal to secant x tangent x plus ln of the absolute value of secant x plus tangent x. So I, which is my original integral, secant cubed, is equal to 1/2 secant x tangent x plus 1/2 ln of the absolute value of secant x plus tangent x. And don't forget your constant of integration c on the end of that. So common integrals here that we're going to use with integration by parts, going to be x to the n e to the ax, x to the n sine of ax, x to the n cosine of ax, x to the n ln of x, x to the n arcsine of ax, x to the n arctangent of ax, e to the ax sine of bx, and e to the ax cosine of bx. Those are going to be ones that we're going to just do a lot of those. So in these cases up here, let u be equal to x to the n, because this simplifies x to the n, and let dv be equal to e to the ax this time, let dv be equal to sine of ax this time, and let dv be equal to cosine of ax this time. Liate takes care of all that for you. If you remember Liate, it tells you what to do. In this case, u has to be ln of x, and dv has to be x to the n. In this case, u has to be arc sine of ax, and dv has to be x to the n dx. In this case, u has to be arctangent of ax, and dv has to be x to the n dx. Again, Liate is going to take care of all this. So in this case, your u is going to be your sine of bx, and your dv will be e to the ax dx. In this case, your u is going to be cosine of bx, and your dv is going to be e to the ax dx. So just go with it until you see the pattern. Sometimes you will have to loop around again like this when you have certain trig functions, but Liate will be your friend with integration by parts. All right, that's it for this video, and we'll come back next time and we'll talk about trigonometric integrals, including this type right here when we come back next time. See you for the next video.